All right, so today as we look at limits at infinity, we're actually going to learn something you already know how to do, you just don't realize it yet. Okay? So, here at the beginning, I've given you three different functions, f of x, g of x, and h of x. And I actually want to use this for kind of a dual purpose here. We're going to learn a little bit about our calculators, but also learn, try to make some inferences here. But what we're talking about here, limits at infinity, we're talking about limits when x is getting huge, when x is approaching positive infinity, or when x is going to negative infinity as well. The same things would apply, but we're going to look at as x approaches infinity. So you notice I made a little table here, and we're going to do f of x together, and then I'll have you guys do g of x and h of x, and we'll fill in these tables and see if we can make some inferences from what we see here. Okay? You can just set it right there. Thanks. All right, so I'm going to go to the calculator here. And, let me bring this up.
So do we plug in?
Where's my calculator? There we go. Okay. So on our calculators, what we're going to do here is, I want to teach you a little bit, kind of an easy way to evaluate functions on your calculator as we're doing this, okay? So if you go to your y equals, okay, we're going to punch in that first function into our calculator. Now, when you're punching in rational functions, make sure that you put the numerator in parentheses and the denominator in parentheses. Okay? So what was that f of x again?
X squared plus 5x minus 4. And then divided by x cubed plus 1.
All right, thank you. Okay, so notice I have the numerator in parentheses, I have the denominator in parentheses. I'm actually not going to graph this, okay? We actually don't even have to graph this. So I'm going to hit second quit to go back out here to the screen. And you see this vars button? We used the distributions menu before, but now we're actually going to use vars. This is where you can access any of the variables that your calculator is going to store. So I'm going to hit vars, and you'll notice there are different variables that we can adjust here, but y vars is what we want to look at. Okay? And what we're trying to do is we're trying to access that y1 that we just stored. I don't know if you realized it, but by typing it in there, it actually stored it in y1. So I'm going to hit enter on function, and you'll notice there's my y1. So I hit enter on that. Now, a cool thing that your calculator will do is that it will treat this as the function, and it'll allow you to use function notation. You know how we write f of x, and you can put f of 3 or f of 5 or f of 10? Well, if I use the y and I put parentheses, and I believe on our table the first thing there was 1, I can hit enter, and notice it gives us the value 2. It will actually evaluate the function that you saved in y1 at x equals 1.
For the inspire, you actually have to graph it, right?
No, well, I think it will automatically graph it for you.
Yeah.
For the nspire, if you want, you actually can use the table feature.
Mm-hmm. Yeah, I know.
And I think if you put the y equals up in that equals box above one of the columns and then type in the columns that you want, you can reference the previous column. Okay, yeah.
What does y1 represent exactly?
It's just the function that you have stored. See how you have y1, y2, y3, y4?
But
This-
what's the number?
It's just a subscript. The first y equals, second y equals, third y equals.
It's like f of x1, f of x2.
Yeah, rather than them putting f of x, g of x, h of x, I of x, j of
But what is,
x.
like, how is that like? I don't get like the number of y.
Serves no purpose other than just to. It's just.
Yeah, it's just distinguishing them, okay?
Oh, okay.
So now, remember above the enter is that entry button. Okay, if I hit second entry, I can change this 1 now to a 10. Okay, and I have 0.34565 and so on. If I hit second entry again, I can change that 10 to 100. Okay. And if I hit second entry again, I can change it to 1,000. I think we went up to 10,000 in the table, right?
Yeah.
Okay?
I'm not sure why. Did you hit second enter?
Yeah, second enter will bring up the last thing that you typed in.
Wasn't it Y1?
Well, it was, but then I changed it. Now, once you bring that up, you can edit it. So I edit it to make it y of 10.
Oh, do you make it every single time just Y of 10?
Yeah, I made that one y of 10, then I brought up y10 and I changed that to y100. I brought up y100 and added another 0. This is a really quick way of evaluating a lot of different values. Okay, so that is how you can do that on your calculator. So now we can use those values in our table. We got, when we plugged in 1, it was equal to 2. And then when we plugged in 10, it was a 0.346, we'll say. When we plug in 100, it's 0.0305. 1,000 was 0.003005. And then here, it came out to 3.000499996 times 10 to the negative fourth. So that's 0.0003. Okay. So as x is getting big here,
Did you see the contours?
The f of x is getting smaller.
f of x is getting smaller and it's approaching what value?
0.
0. Okay? It's getting closer and closer and closer to 0. Okay? Now, let's say front row, why don't you guys work with g of x, and back row, why don't you guys work with h of x and fill out this table, and then we'll make some inferences from this. Okay, so let's go through g of x here. We've got these, what did you guys get when you plugged in 1?
0.5.
0.5? And how about 2?
2.89.
3? Or not 2. 100, sorry.
30.
32.79, okay. 1,000,
33.
0.779.
okay. All right, and when you put in 1,000 or 10,000,
3330.
I got 3332.
I just did 6 things.
okay. So yeah, 3 sig figs would be that. So what do you see is happening to this number?
It's going up.
It's going up, all right? So if we kept punching in bigger and bigger and bigger numbers for x, what will probably happen?
It'll get to infinity.
It'll go towards infinity, right?
Oh, that's what you mean for the previous one. I was like, why did you put in 0 there? I was like, okay, we're not anyone like this one. We did f of x.
Oh.
We did an error.
Oh, yeah. No, it's approaching 0. If we kept going, we would go towards infinity. If we kept going with this, we'd get numbers that were continuing to get smaller and smaller and smaller, closer to 0. All right? So now, back row with h of x. What do you get when you plug in 1?
0.0357.
Is that right?
Yeah.
0.0357. Okay.
Next one. 0.516.
All right, 100,
0.6003.
1,000,
0.6001.
and how about 10,000?
0.60002.
All right, so what is this approaching?
0.6.
It's approaching 0.6, right? It looks like it, at least, you know? Looks like it's getting closer and closer and closer to 0.6.
Didn't it already reach 0.6 though?
Well, not quite, it's at 0.60002.
Oh, like it already passed 0.6, right?
No, we haven't got it. Notice, well, in this case, it was below, and then it jumped above 0.6, but now it's approaching. Now it's like coming back down towards 0.6. So, like the graph on this one, you know, it would go up above 0.6, but then it's coming back down towards 0.6. Okay.
So it would just be a hole the first time it passes?
Actually, no. At some point, it would actually equal 0.6. All right. We'll see this in a second, though. What do you notice here, though? This is approaching 0, so we could say the limit of f of x as x approaches infinity would equal 0. Okay? The limit of g of x as x approaches infinity, it's going off to infinity, right? So what would we say about the limit there? It does not exist, okay? It approaches positive infinity, so we would say it does not exist. Okay?
So when it's approaching positive or negative infinity, that does not exist, right?
Yes, you say that the limit does not exist because it's not approaching a specific value, okay? Remember we said depending on what book or website you look at, some of them just say infinity or negative infinity, others say doesn't exist. IB and AP both do does not exist, so that's why we're teaching it this way. Where I went to college, we learned it as infinity, negative infinity,
But x can approach infinity.
X is approaching infinity, yes. There, it just means that X is getting bigger and bigger and bigger and bigger. So, all right, so now here, h of x, the limit as x approaches infinity would equal what?
0.6.
0.6. Now what's 0.6 as a fraction?
6/10, 3/5.
Yes, there we go, 3/5. Now, do you guys happen to notice something here? Making a connection?
The first like coefficient it's like 3/5 in the function.
Okay, yeah, you see here, it's 3/5, right? But we didn't do that on all of them. Like g of x wasn't 1/3 and f of x wasn't 3/1.
Figure out one.
They don't have this.
Zero above.
Oh, we're making connections now. Okay, so h of x, we had the same exponent, we have the same degree, right? So we use the ratio of the coefficients. Okay? Evan mentioned Bobo. Bigger on bottom, 0. Okay?
I remember him. Oh, yeah.
And how about g of x?
Bottom.
Bottom. Bigger on top, none. Now, so if the degree is bigger on the top, the limit does not exist. Alright? Now, what context did we learn this in before?
Mr. Griffin's class.
Asymptotes. You learned it in my class too.
No, Mr. Griffin's class.
Last year? Oh, first. Yeah. We'll give credit's due. Alright. So, but what were we learning about, Evan?
Asymptotes?
Asymptotes. Which kind of asymptotes?
Oh, horizontal.
Horizontal asymptotes. which remember, horizontal asymptotes deal with end behavior, okay? So, this is how, for g of x, notice how it jumped up, or I'm sorry, h of x jumped up above the 0.6, but now we have this horizontal asymptote at 0.6, okay? That's because if you remember, we just talked about this very briefly last year. But when you have horizontal asymptotes, it's actually possible to cross over the asymptote, and that's a terrible drawing, but you get the idea, okay? It's actually possible to cross the asymptote in the middle because the asymptotic behavior is on either end. It's as x goes to negative infinity and as it goes to positive infinity, okay? In other words, the limit, the value it's approaching is that asymptote, okay? So, that's the connection I wanted you guys to make, and that's why we did this little table and all of this, because I wanted you to make that connection. Here's what we just summarized. If the degree in the numerator is bigger, the value is going to go to either positive or negative infinity. So we will say that the limit does not exist. Okay? This is bottom. Bigger on top, no limit. Alright? If the degree in the denominator is bigger, the limit it approaches 0. So here's the bobo. Bigger on bottom, 0. But then we had that if the degrees are the same in the numerator and denominator, then the limit is the ratio of the leading coefficients. Okay? And guys, here's the thing. The reason why all this works, the reason why we can look at just that first term is because if you're looking at, say, an x squared as opposed to an x cubed or an x or even just a constant like 1,000, when your x values are very small, the differences between these aren't that great, okay? However, when x starts getting big, obviously 1,000 just stays 1,000. X just becomes whatever x is, but it's only going up by 1 at a time. Your squares increase a whole lot more at a time. We're going from 1 to 4 to 9 to 16 to 25 to 36, 49. It's increasing much faster than just 1, 2, 3, 4, 5, 6, 7. But the cubes go even faster. They grow even bigger. They're going from 1 to 8 to 27 to 64 to 125 to 216. I think that's about as far as I can go right now. Oh wait, no, 243. I think that's 7 cubed. But anyways, you've got 343. This is going to grow really, really, really fast. So as x gets enormous, how big is x squared compared to x cubed?
Very little.
It's very little. Okay? So that's why when we look at something like, a 3x squared plus 5x minus 1 over a 7x squared plus 6x plus 1,000,000, okay? It doesn't matter that there's this million here because when our numbers start to get big, the x squareds are so much larger than the rest that all of this really just becomes irrelevant. Okay? They're so minuscule compared to 1 billion squared, So now we have 3 times 1 billion squared over 7 times 1 billion squared. Well, that's 1, so it's just 3/7. Okay? That's what the limit will approach. Okay?
But that's only when it grows like infinity or negative.
Yes, that's only when x is approaching infinity or negative infinity. That's why we're looking at limits at infinity here. Okay? This slide I'm going to kind of skip over. This gives us a little review of some algebra topics that are behind this. You can take a look at those later on. But let's look through a few examples here just to kind of solidify this in our minds. We have the limit as x approaches infinity of x squared plus 3x plus 5 over x cubed plus 1. So what would our limit equal? Why?
Oh, wait. Is it bigger on the bottom than a 0?
Bigger on the bottom, good, you caught yourself there. Bigger on the bottom, the cube is bigger, so this limit's going to approach 0.
And since the next one, x squared is the same on the top and bottom, so it's 3 sevenths, right?
Okay, good. Here, we have the same x squared and x squared. So, this 4x minus 5 and this minus 2x plus 11, those are irrelevant once our numbers get so huge. So we're just looking at those leading coefficients, 3 sevenths. Okay? Here's a fun one. Okay? What's the degree on the top?
-1.
A half. And the degree on the bottom is a half as well. So,
Wait, what?
2. Right?
yeah, it's 3 over 2. Okay? Again, we can ignore that minus 1 because when our numbers get huge, a minus 1 means nothing. But the degrees here are both a half, so I can just look at the ratio of the coefficients again. Okay? Alright, here's one. Let's try it on the calculator.
Oh wait, it doesn't exist, right?
No, it actually does exist.
Bigger because x over x is correct.
But how can we
No.
tell?
Well, yes. I'm not.
How can we tell how calculated?
Well, if you punch in 1 plus 1 over x, all to the x power in your y1, and then you could just do what we did before, do y1 parentheses and put in like 1,000,000 in there or something.
2.718.
You got 2.718 and so on. Does that look familiar?
No.
Is that like E or something?
It is E, alright? I had to throw this one at you.
He just got so excited.
That's E, okay? So guess what?
Is that E or like whatever?
So guess what? This one doesn't follow any of the rules we just learned, okay?
Awesome.
It's a curveball.
It is a curveball, alright?
Yeah.
So listen, not every one of these is gonna work just using that nice easy little 3-part rule, okay? There might be some where the only good way is really just to plug it in and see what it approaches, okay?
So what if you don't know that 2.718 is equal to E? Would it be wrong if you just put 2.718?
I don't think it would be necessarily marked wrong, but you might miss a connection that you need to make later or something. That though is the definition of the number E, okay?
Is the next one, is that 3
Alright, let's look at our next one here. We have the limit as x approaches infinity of 3x squared plus 4x over 5x squared minus 7 plus 6. So how are we going to handle this one?
Convert it into
Isn't it-
one big fraction.
Isn't it just
We
3
could.
over 5?
But there's actually a simpler way. What?
Isn't it just 3 over 5 plus the units?
Okay, so you're saying just make this 3 over 5.
Yeah, if we have the 6, we just do the first power.
Okay.
Well, the 6 won't matter because it's so little, right?
Wait, hang on. Wait, what were you saying, Evan?
Does it like translate the limit with it, that extra 6?
Ooh, there's an interesting thought there. This would translate this whole function up 6, right? So wouldn't your horizontal asymptote get shifted up 6 as well? So what would our limit equal? 33 over 5 or 6 3/5. Now, Yeah.
I'm sorry, probably really stupid, but isn't that like the vertical shift, the 6?
It is. But remember, our horizontal asymptotes are y equals.
That is true, okay. Gotcha.
Now, watch this. We actually learned how to handle this already, but you may have forgotten because it was Friday. All right, so
Really?
we have 3x squared plus 4x over 5x squared minus 7, and we'll end with this here. The limit of a sum is the sum of the limits. So guess what I can do? I can take the limit of that and then add the limit as x approaches infinity of 6. Well, that's the limit of a constant.
Which is just a
Damn,
constant.
you're so
So that is the constant. So yes, this first part is 3/5, but the limit of a constant is the constant, so that's 6 3/5. So, recognizing the vertical shift is excellent. You can also use the limit theorems we looked at on Friday to break this down and work with it as well. Okay?
Is
Yes?
it possible to do a horizontal shift?
Yes, but will that affect our horizontal asymptote? No.
Right.
Okay? So yes, it's possible, but that's where your understanding of functions and what will impact what
What would
makes a
that look
difference.
like? Like what would be a horizontal?
If I, like, instead of the x's, if I put like an x minus 2
Oh,
in
right.
all the places where the x's are, that would shift it to the right 2
But it
spaces.
wouldn't matter.
But it wouldn't impact our limit. All right, great job, guys.